2.5 years ago, MIT entered into a research agreement with startup company Commonwealth Fusion Systems to develop a next-generation fusion research experiment, called SPARC, as a precursor to a practical, emissions-free power plant. Now, after many months of intensive research and engineering work, the researchers charged with defining and refining the physics behind the ambitious reactor design have published a series of papers summarizing the progress they have made and outlining the key research questions SPARC will enable. Overall, says Martin Greenwald, Deputy Director of MIT's Plasma Science and Fusion Center and one of the project's lead scientists, the work is progressing smoothly and on track. This series of papers provides a high level of confidence in the plasma physics and the performance predictions for SPARC, he says. No unexpected impediments or surprises have shown up, and the remaining challenges appear to be manageable. This sets a solid basis for the device's operation once constructed, according to Greenwald. Greenwald wrote the introduction for a set of 7 research papers authored by 47 researchers from 12 institutions and published today in a special issue of the Journal of Plasma Physics. Together, the papers outline the theoretical and empirical physics basis for the new fusion system, which the consortium expects to start building next year. SPARC is planned to be the first experimental device ever to achieve a burning plasma, that is, a self-sustaining fusion reaction in which different isotopes of the element hydrogen fuse together to form helium, without the need for any further input of energy. Studying the behavior of this burning plasma, something never before seen on Earth in a controlled fashion, is seen as crucial information for developing the next step, a working prototype of a practical, power-generating power plant. Such fusion power plants might significantly reduce greenhouse gas emissions from the power generation sector, one of the major sources of these emissions globally. The MIT and SPARC project is one of the largest privately funded research and development projects ever undertaken in the fusion field. The SPARC design, though about twice the size as MIT's now retired Alcator CMOD experiment and similar to several other research fusion reactors currently in operation, would be far more powerful, achieving fusion performance comparable to that expected in the much larger ITER reactor being BOO. The high power in a small size is made possible by advances in superconducting magnets that allow for a much stronger magnetic field to confine the hot plasma. The SPARC project was launched in early 2018, and work on its first stage, the development of the superconducting magnets that would allow smaller fusion systems to be built, has been proceeding apace. The new set of papers represents the first time that the underlying physics basis for the SPARC machine has been outlined in detail in peer-reviewed publications. The 7 papers explore the specific areas of the physics that had to be further refined, and that still require ongoing research to pin down the final elements of the machine design and the operating procedures and tests that will be involved as work progresses toward the power plant. The papers also describe the use of calculations and simulation tools for the design of SPARC, which have been tested against many experiments around the world. The authors used cutting-edge simulations, run on powerful supercomputers, that have been developed to aid the design of ITER. The large multi-institutional team of researchers represented in the new set of papers aimed to bring the best consensus tools to the SPARC machine design to increase confidence it will achieve its mission. The analysis done so far shows that the planned fusion energy output of the SPARC reactor should be able to meet the design specifications with a comfortable margin to spare. It is designed to achieve a Q factor, a key parameter denoting the efficiency of a fusion plasma, of at least 2, essentially meaning that twice as much fusion energy is produced as the amount of energy pumped in to generate the reaction. That would be the first time a fusion plasma of any kind has produced more energy than it consumed. The calculations at this point show that SPARC could actually achieve a Q ratio of 10 or more, according to the new papers. While Greenwald cautions that the team wants to be careful not to overpromise, and much work remains, the results so far indicate that the project will at least achieve its goals, and specifically will meet its key objective of producing a burning plasma, wherein the self-heating dominates the Na. Limitations imposed by the COVID-19 pandemic slowed progress a bit, but not much, he says, and the researchers are back in the labs under new operating guidelines. Please support our channel to grow by pressing subscribe button as well as the bell icon for daily science updates. Thank you.